Okay, so first on the introduction to image segmentation problem. Okay, so here a typical computer vision problem. We have object detection problem. We have the classification and localization problem. Like to classify the image to be one of various classes, and then we had to localize the part of the image that make up that classification. So for example, here we need to define that, okay, that is about the cat, and then localize the cat version in the image, right? And we have the problem that we discussed today is a semantic segmentation problem. So in that problem, we had to somehow classify every pixel in the image, so that pixel will be classified into one of predefined classes. For example, here we define 4 classes: grass, cat, tree, and sky. And our objective in that semantic segmentation problem here is to classify every pixel in the image to be either grass, either cat, either tree, or either sky, right? So no object, but just the classification of pixel in the image, right? And we have other problem that may be related to the same segmentation. Here we have instant segmentation. So the output is to not only classify the pixel in the image, but also to be able to distinguish which pixel belong to which object, right? So for example, here we have 2 dogs and 1 cat, and we need to recognize every pixel belong to a dog, and then also the cat, right? So we don't mix the pixel in the 2 dogs together, right? Okay. So in this slide, that to make things clear for you on the image segmentation problem. First, classify a pixel into predefined classes in the image, and we do not distinguish the object of the same class in the image, right? So for example, here, if we have this is the beginning image, right? Input image have 2 count, then the output of the segmentation is just to classify the pixel into count. So we don't distinguish the pixel belong to the first count or the pixel belong to the second count. Okay. So the application of image segmentation could be for satellite and aerial image processing. So for example, here we have the image captured by the satellite, and we want to somehow classify the pixel into the building, into the tree, or into the road, right? Okay, and here is the application of image segmentation in autonomous vehicle. For example, when the Tesla vehicle moving on the road, it had camera that capture the environment in real time, and of course, the car have to somehow process the image and detect segment the image into different type classes: the pupil, the road, the sidewalk, and the tree, and all the car, right? Okay, here is another example of the problem in healthcare system. For example, you can have the X-ray image that capture the lung of the patient, and then you want to somehow classify the pixel belong to some specific disease, right? So that cancer and whatever, right? And also another example of healthcare processing for the this is a X-ray for the brain, right? Okay, and also for a very typical and popular application in image processing is OCR or OCR problem, optical character recognition. You somehow need to convert a scan image of a document to be a digital version of that document, right? Recognize the character, the word in the document, right? So one of the tasks in the OCR process is to somehow, classify the different region of the image to be either text, finger or table, headline, whatever, right? And then you can do the OCR on that, specific text region, right? Okay, so the approach for this problem could be in the past people thinking about the using sliding window approach to do that image segmentation problem. So in order to classify every pixel in the image, you you analyze the location around the pixel to have a specific window, right? And then in order to classify, for example, the pixel in the center here, you analyze the surrounding of the pixel to have a specific window, right? And then you can put it, this window into the CNN network, and then have the network to output the classification of that window, right? So to do the classification for every pixel, you need to move the window. You have to slide the window from left to right and from the top to bottom, right? To bottom, right? Okay, so this approach is not very efficient, and it not reuse the share feature between overlapping patches, right? For example, when you move the pixel from this location to the label pixel, so that the surrounding window doesn't change much, right? So, but in the way you're doing like this, you don't reuse the share feature between overlapping patch, so it's not efficient, right? Okay, so now we have another idea to do semantic segmentation is to use a convolution network, right? Neural network to do that semantic segmentation. The idea is to encode the entire image with the convolution neural network and to do the semantic segmentation on the top, right? For example, here we have the input image with the specific size and 3 channel. We put the entire image into the convolution network consist of different convolution layer, right? And then we have the final activation map with the same size as the input image SW, right? And then we can do the do the prediction over that final activation map, right? To predict, okay, if that belong to the cow, that belong to the grass, or that belong to the tree, right? Okay. So if we use that approach, we have this problem. The classification architecture often reduce the future spatial size to go deeper, right? But the semantic segmentation requires the output size to be the same as the input size. In a typical convolutional neural network that we use in previous lesson, we always, seeing that, okay, after a couple number of convolution layer, we have the activation map have to actual smaller size than the input image, right? So the idea here is to somehow being able to use a convolutional network, but still keeping the size of the activation map to be the same as the size of the input image, right? So if we if we, I mean, if we use a convolution layer that keep the size of the output at the same size as the input, right? Then the convolution will be a bit expensive, right? So somehow we can think about this. We somehow reduce the size of the activation map when we for the input image, and then at some point we can enlarge the activation map, right, to make the prediction for every pixel, right? Okay, so we come up with a better idea of designing the network as a bundle of convolution layer, and with both the downsampling and upsampling inside the network, right? So the downsampling is a part that we already familiar with in the previous lesson, right? And now we discuss about the way we can do the upsampling in the convolution way, right? Okay, the mechanism that downsampling the inputs could be the polling layer, or we use the tri-convolution layer, right? Okay, and now we discuss the way we can do upsampling. Okay, so now we discuss the upsampling layer that we use in the network for image segmentation problem. The first layer we can use is to use the unpooling layer, and the layer have no parameter. So look into the example we have in the slide. This is the input image has a size 2 by 2, right? And we want to enlarge the image to have a bigger output, right? With a size 4 by 4, right? So this is the idea of unpooling. We can somehow replicate the value of a value in the initial input to be, I mean, to be at the 4 location in the output. For example, here the 1 here can be replicated in this region, the 2 here we replicate into this region, and the same for the number 3 and number 4, right? Another way to do unpooling with no parameter is to use the backup null mechanism. So in this mechanism, we can keep that value in the input, right? That's location, and then for other missing value, for other locations that have missing value, we can fill the number 0, right? For example, there is the value here, and then this missing location we can replace with 0, and the same for this and this, right? Okay, so we can also use a map unpooling layer So for the mark unpooling layer is this okay, so before discuss the mark unpooling layer, I will remind you about the mark pooling layer, right? So for the mark pooling layer, when you do the mark pooling, you have the input with the size 4x4 here, and then you keep the mark to in the output 2x2. Okay, so in this region the mark is 5, you keep 5. Okay, in that location the mark is 6, you keep 6, and then for the 7 and 8. So the mark unpooling is that the inverse case for the mark pooling. So you somehow first I mean, when you do the mark pooling in the previous layer, you can remember which element was the mark. I mean, the location of the element was the marks, right? And then on the corresponding mark unpooling layer, you can use the position from the pooling layer to do the mark unpooling, right? For example, in the previous, the mark was in that location, and now okay, you replace that location with the value, and then for number 4 also, and for other location, okay, you can keep 0, right? So in this in order to use mark unpooling, you need to have this is a condition to have. You need to have the corresponding pair of downsampling and upsampling layer, right? So that, I mean, when you do the mark pooling, you need to remember the location at which location the element was marked, and then for the corresponding mark unpooling layer, you use that that safe location to actually know where to replace the value when you do mark unpooling, right? Okay. So the way we use unpooling and mark unpooling here is a layer that have no parameter, right? So no way to learn, and the way we unpool the input is somehow strict, and it's not flexible, and it might not be might not be efficient, right? So we want to have a way that have the unpooling layer that can have learnable parameter, right? Okay, so here we discuss the transfer convolution that actually do upsampling with a learnable parameter. That means that the parameter of that convolution layer is learned during the learning of the neural network, right? Okay, so we discussed about the normal convolution on the input with a size 4x4, and this is a size the convolution 3x3, this try 1 and parting 1, and the output has the same size as the input, right? Okay, so the way we do the normal convolution is that apply the filter at a specific location, and then we do dot production between the filter and output, right? And then we calculate the value at that corresponding location in the output activation map, and then we move the window, and then we again, right? So in the case we have the tries 2 and parting 1, we have the output activation maps that is smaller in size compared to the input with the size number with the size 4x4, right? Okay, right. We again do the dot product because and then with the strike equal 2, we moved two block rather than moving that's one block, and that why we have the output of the side 2 by 2, right? So in this case, because the output after the normal convolution with the strike 2 here reduce the input side, right? So we can actually interpret the strike convolution as learnable downsampling, right? Learnable downsampling because the weight of that convolution is learned during the training, right? Okay, so now we discuss transpose convolution. So transpose convolution is an upsampling mechanism that contains trainable parameter, right? So take a look into this example. We have 3 by 3 transpose convolution with the strike 1 and padding 1. We have the input with the side 2 by 2, and we by applying that transpose convolution, we expect to have the input with side 4 by 4. Okay. So here's the computation of transpose convolution. Okay, so we take the this element in the input, right? And then the input here will be used for as the weight for the filter, right? And and we multiply the input here with the element in the filter, right? And then we fill up the value in the output activation map, right? And then when we move the the filter, right, the convolution, the transpose convolution filter, we use another value at the weight for the filter, and then we multiply with every element in the filter, right? So for the part that have overlap, we can sum the output overlap, right? So by using that transpose convolution, we can actually enlarge the input. For example, here we enlarge the input side 2 by 2 to have the output side 4 by 4, right? We actually use the input element to be at the weight for the filter, and we multiply the weight for every location of the filter, every element in the filter, right? Okay, so a transpose convolution can have other name such as up convolution, fractionally strike convolution, backward strike convolution. You can use it as a deconvolution, but we should not, because it's easy to misunderstand. It's not convolution. So transpose convolution is convolution operation, right? So here the transpose convolution for one-dimensional input. For example, we have the input with side 1, 2, like this one, and we have the filter with side 1, 3. Then we can actually multiply the input with every element in the filter, AR, AX, AY, AZ, right? And we put it here, and when the filter moves to the next location, we multiply the value B with every element in the filter, BX, BY, BZ. So we have the overlap in here, so we can actually compile the we can zoom the overlap output, right, to be here AZ plus the BX, right. Okay, any questions so far? Okay, so the convolution can be considered as magic multiplication. So we can express the convolution in terms of magic multiplication as in this formulation, right? So this is a 1D convolution with kernel size 3, stride 2, and padding 1, right? And the convolution transpose multiplied by the transpose of the same matrix, right? So it could be at this formulation for the transpose convolution, right? So in this example, we have the 1D transpose convolution with kernel size 3, stride equal 2, and padding 0, right? Okay, so to recap about semantic segmentation with convolution neural network, we can design a network as a bunch of convolution layer with downsampling and upsampling inside the network, right? So that we somehow, I mean, in the beginning convolution layer, we can reduce the size of the activation map, and then in the in the second part of the network, we can have the upsampling layer that can actually enlarge the activation map, so that in the final layer we can do the prediction for every pixel in the every corresponding pixel in the input. Okay, any question? Okay, so we can have break of 5 minutes and then we will continue. Okay, so let's continue. So here we discussed different objective function for image segmentation problem. We can see here different type loss. So this is a distribution based loss, right? Okay, for the distribution based objective function, we can use a binary cross entropy loss function, and the formulation for binary cross entropy loss function is here. Okay. So because you and for the
Em cho thầy cho share slide.
just a slide. Okay. Okay, so do you see my slide? Okay, so let me remind you about some concept that we use for that loss function. So first is the concept about the information E. It's just like the minus the log P, right? And then we had the concept of entropy, and when we had the KL division, is actually to measure the difference between the two distribution P and Q, right? So the cross entropy is actually of P and Q is actually the entropy of P plus the KL division of P and Q, right? So when we minimize the cross entropy here, we actually somehow minimize the KL division of P and Q, right? So for binary cross entropy, we have that two value, 1 or 0. So when we apply into that specific situation, we can actually have this formulation, right? Minus y log y hat plus 1 minus y log 1 minus y hat, right? So it's actually this is y hat here is a Groucho's value, and the y can receive the value from 0 to 1, right? Okay. So we can have one extension of binary cross entropy loss. Its name is weighted binary cross entropy loss. So we can use that the beta hyperparameter here for the weighted binary cross entropy. In that weight here can be used actually to tune the fail negative and fail positive, right? If you want to reduce the number of fail negative, then you can set the beta to be a value bigger than 1. And if you want to decrease the number of false positive, you can set the beta to be smaller than 1, right? You can also use the Fokker loss. And the Fokker loss here shows the problem of last imbalance between the background layer and the objective layer of interest. So the loss downweight the contribution of easy sample and enable the model to focus more on learning hard example. And this is a formulation for the Fokker loss. If you have that gamma parameter to be 1, then it works like the cross entropy loss, right? So the alpha is a hyperparameter that you can generally choose from in the range from 0 to 1, right? So you see here you have the p hat power gamma. So if you have the gamma so you have the gamma is big, then somehow that p hat gamma will become, I mean, 0 if that p is less than 1, right? Okay, so besides the distribution by objective function, you can use area by objective function. It actually uses the overlap between the ground thrust and the prediction, right? So one loss you can use here is a dice loss. So okay, so die loss here is computed this way, right? And and you can use the transcript loss, and it's another one type algebra by objective function you can use, right? You can combine the objective function of different type, such as the die loss plus the cross entropy loss and die loss plus Fokker loss, right? So it's just to I mean, make the sum of, I mean, the complement loss, such as the CI loss plus the dice loss, right? Another loss function, advanced loss function that you can use is a binary based loss function. So it actually use a distance metric on the space of the contour, not in the routers and the prediction, and not the region, right? So the idea here is to somehow, I mean, minimize the differences between the contour of the culture and the distribution, and it is formulation. I will not go into the detail about this loss, but if you are interested in that loss, you can take a look into the paper on binary-based loss, right? Okay. So any question for the loss function? Okay, so let's have 10-minute break and then we will continue. Okay, so let's continue. So now we discussed some typical image segmentation network that you can use today. Okay, so first we discussed the fully connected. Did fully convolutional neural network with two shortcuts, right? So you are seeing here, this is a part of a convolutional network that you have multiple convolution layer that are actually down sampling the input image to be activated map with smaller size, right? And then you actually have the upsampling layer that do the enlarge thing of the activation map, and then you do the prediction on that last final activation map, right? You have two shortcuts. So the shortcut is thing you use in the residual neural network, right? So actually you don't use only the information in the last convolution layer, but you also use the information in the intermediate you also use the activation map of the intermediate convolution layer. For example, here you take the activation map of that position, and then all right, you combine with this is upsampling of the last convolution activation map, right? You upsampling and then you combine with that, and then you also do the upsampling again, and then you combine with the activation map in the in another intermediate position, and then you combine again, and then you have the final activation map. That way you can use the sum mark for the prediction, right? Okay, so this is a mark pooling, this is the prediction, and it is a deconvolution, the transport convolution layer that I showed you in the beginning of the lesson, right? Okay. Okay, so yes, is another illustration of a fully convolution network with different level of resolution, right? So this is the image, and then you have the convolution layers. Number one, pooling layer one, another pooling, then okay, right. And for example, this is the output of the pooling layer number 5, and then you can do the upsampling 32x upsampling, right, to have this final activation map here. And you can also do just only 2x upsampling prediction, and then you combine with the pooling output of the pooling number 4, right? And then you have the 16, and then you do 16 x upsampling prediction, right? And you also can combine with the further activation map in the beginning of the convolution network, right? For example, you use the output of the pooling 3, and then here you get the you get the output after the combination of pooling 5 and 4, and you do 2x upsample, and then you combine with the pool 3 prediction, and then you do S time upsample prediction here. Okay. So this is a result when with different configuration, right? So if you just use FCN32S, it's only data output. You had did the final result, but if you use that output, right, then you have better result in compared to the Gaussian segmentation map, right? Okay, so here we have another network that can be used for image segmentation problem. Its name is UNet, and this UNet is widely used in medical image processing. So for the UNet, you have the network that consists of two parts. Two part, right? So the first part is like the downsampling, and the another part is upsampling. And the downsampling, its name is contraction part, and for the upsampling, its name is expansion part, right? So for example here, for the UNet on the contraction part, you have the input image here with the size okay, these are 572 by 572, right? And that input will go to the convex 3x3 and value activation, right? And then you downsampling again by you downsampling the output by using the map pooling 2x2, right? And then again you put you have another convex 3x3, the ReLU, right? And then you map pooling again, right? And here then we start the expansion part by doing the upsampling by using the uppooling convolution layer here, and then using the shortcut add in the Fourier convolution network, right? You combine with the activation map of the corresponding layer in the contraction path, right? And again, on the way you do upsampling, you combine with the output of the corresponding output of the downsampling layer, right? Okay. So because the size the size of the output after the sampling here, and the corresponding activation map in the contraction part is different. So on the way you do the shortcut, you need to clock to be the same size. For example, here the size here is so for example here the size 136 by 136, and you crop to the size 104, right? And then you combine with the output of the up convolution layer here, right? So again for this shortcut, you also need to cross to have the size 200 by 200, and then you combine with the output of the activation by the up convolution layer, and again for the last one, right? Okay. Any question? Hello. Any question? Okay, then we can continue to discuss on the UNet++. So the idea of UNet++ is to bridge the semantic graph between the future map of the encoder and decoder prior to fusion, right? So for example, here, when we discuss about the UNet, right? At that point, for example, you need to combine, I mean, the output of the at this point, you need to combine the output of the up convolution layer here with the activation map of the corresponding layer in the construction path, and you see that the information contained in that in the output of the up convolution 2 by 2 here, it might be totally different from the output of the activation map in that location. So by combining like this, I mean, somehow it could be I mean, two different things. Of course, it has the same sign. It has the purpose to somehow exploit the information in the farthest activation map. But the combination here is a little bit, I mean, unnatural, right? So the UNet++ bridge the semantic gap between the future map of the encoder and decoder prior to fusion by instead of combine, I mean, directly this, I mean, output to that output, you have, I mean, different, I mean, block here to actually reduce the gap, the semantic gap between the layer in the encoder part and the layer in the decoder part, right? So it have this is the black bond of the encoder, right? And then you in this you do down sampling, and then you do up sampling, and you have skip collection at in the visual network or in the UNet, normal UNet, right? And you have different block in here to reduce the gap, the semantic gap between the encoder and the decoder, right? And you also exploit the deep supervision by having the, I mean, by having the loss that I mean, having the lot on not only the last output layer, but also the I mean the intermediate output here. Okay. We have another type network. Its name is stacked UNet and CUNet. So for the stacked UNet, you actually stack many UNet in series and use that as a single network for training, right? For CUNet, you also stack many UNet in the series, but there are additional short connection between the unit. This is a shortcut to make the information flow better from the beginning of the network to the, I mean, end of the network, right? Okay. Okay, so do I have any question? Any question? Okay, then we can break for 5 minutes, right? Okay. Okay, so I think that we can practice a little bit on image segmentation problem. So I just send you the link to a Colab notebook where we can see the code for the UNet network implemented in PyTorch. So let's try to understand the notebook and run it step by step. You have around 15 minutes to work with the notebook, and then I will ask one of you to explain the explain to see if you understand the code of UNet and the way you execute the code. Okay. Actually, you can just start with that the next notebook where you try the vanilla UNet implementation. In the first link I send you is the UNet redness, so it's a little bit more complicated network. Right? So let's try the first, try the second one. You can continue with another notebook that I send you in the chat. Right. Okay, so let's do some discussion. How it's going? Is there anybody that willing to discuss on the notebook number 1? Lê Trường Giang.
I'm here. Can you hear me correctly?
Yes. So can you discuss a little bit on the notebook number 1?
Look number one. Okay, let me share my screen.
Okay. Good.
Do you see my screen now?
Yes. Okay. So discuss the UNet Redness notebook. Okay, so I think it's not in Rednet is something you already learned. Okay, so let's start.
Actually, I just
Yeah.
finished the running. I see the result here. Actually, I still notice they use the NARS that actually so here.
Okay.
To be honest, I do not really understand about the mathematical behind this loss. They use the BCA weight and something like trade-off between BCE weight, BCE loss and die loss.
Yeah, so it's actually the way they combine the BC loss and the die loss, and the
Yes.
BC weight is here is that true? I mean, it's a common mechanism people use to combine. I mean, two things.
So the BCA weight is 0.5. I think it's the hyperparameter, and they put it, but I don't understand why they use this number.
I mean, so
Actually.
if it's a 0.5, and you see the loss would be half the BCE loss and a half dice loss, right?
Yes.
So is that the mechanism? If you change the weight to be 0.9, then you see 90% is the BCE loss plus 10% dice loss. See?
I know that was actually is come from the practical that this value is always have a two good results, right? Or just
It's not the hyperparameter that you can do many experiments to see which hyperparameter to use.
okay. Let's see. Actually, I see here there's the loss is not decreasing so much. Maybe they use a pre-trained bond model. Then I see the loss not decreasing so much.
Okay, so maybe we can try to start from the beginning. You explain a little bit about the course so that everybody can learn from you.
About it's at the beginning, okay.
Yes, right.
So about this cell, is actually nothing much to say. Just import TUT and try to get GPU environments. And here we see they import the simulation. It's actually the Python code they use to generate the data set, the fake data set, to generate the image and the target image. It just the number and randomly. So I don't think it had too much thing to say. Yet also they visualize the image that just simulation with simulation file. You see that here is the fake data set they use to train the model. And then also get the sim data set, actually get the input of the simulation image we just talk about and load it into the data set and get the data loader. Just this. The reverse transformation, if I understand it correctly, that when you output of the model, it will be something like a ray image or not the color image. So the reverse transformation that you can form another change the mean and standard deviation image to come to have it original image to similar to input of the model, if I understand it correctly. And here the code of model. Did I need to explain about the code of model?
Yes.
But what kind of me need to explain to them? But how to see that I need to have special here? Just have layer, sequential, and the code cards, which is like we just studied about in the lecture.
Okay, so I think you can if you don't know how to explain clearer, then I think we can continue.
Yes. Okay, this is they call the class model and push them into the GPU. I mean the device if the GPU is available. As you see the some summary of model here. Also, when they use the summary of library to see to save output of X layer. And this model is quite big because the total parameter is 28 million parameter. Is quite big, really big is in my view. Compared to the other here, I mean the second collab you sent to us is just about I think the 7 million parameter. It's really big. So also they build the module to calculate the noise, the thing we just talked about. And just the print function and the train model here. Use the code here. They use 50 epoch. And I see that the training phase, nothing special. It's just normal. You put the model, put the image to the model, and they calculate the loss and type what the loss and optimize the tab. Is quite similar to we learned before, right? And I don't see any special here. Like also the schedule step. Let me see what is schedule here. Only put the schedules below. Okay, they use the learning rate scheduler is tab scheduler here, and they update the learning rate epoch. So that's it. This trainer model, and we see the result here. The below of the train model, I say you test some image. I see for understand how the model the result after retraining. But that's it.
Okay. Could you show the code about the upsampling layer?
Upsampling layer. Okay. Here we do the and upsampling layer with scale factor 2. That's actually we room the pixel into the bigger the spectral issue.
Yes. So do you want to go into the detail about the upsample function? Or maybe we can try to see the documentation of this.
Okay, maybe I try to use a document. Yeah, it is the document of the NB upsample.
Okay.
Since
okay, so any question from other of you? Okay, so thank you very much, Zhang. So I think that we will have more time for other people to discuss on the progress. Thank you very much.
Yes.
Okay, let's ask again. Nguyễn Thị Trang. Hello. Trang ơi. Ok. Nguyễn Minh Châu.
Vâng ạ, theo em tí ạ.
Okay. Thank you.
Em thấy màn hình em chưa?
Thấy rồi em.
Vâng ạ. Thì okay, so I just finished with the classical UNet. So I will start with my notebook here. The first step is to clone the GitHub repository, nothing special. This is importing and to test if to try to generate a fact data set, 3 sample here with the mask and the actual images. And here we declare the data set, sim data set. Actually, we call the function generate random data from the model that they declare here. Here, they just use NumPy and randomize some images with shape. So after that, we have a data set that we just generated, and we declare the data loader here, nothing special. Batch size equal to 25, and as you can see here, the train data set has 2,000 samples, and they declare the reverse transform here. I think it is the reverse function of the function transform that we used in the data loader. Where is this? The transform here. Yeah, because I think that the generated image will have a grayscale from I mean not color images, so we try to reverse the grayscale images to color images with this function. I know. I'm sorry. I think it is trying to transform the image to grayscale, because as we can see here, it clamped the image pixel from 0 to 1, and then they multiply it by 255. Okay, so here they summarize the model. As you can see that the total parameter is just 7.8 million. It is not a big model, and they use the same loss as the other notebook, which is the combination of binary loss, binary cross entropy loss, and the dice loss, and with the weight of 0.5. And the print function, and they declare the training loop. nothing special, just feed the data through the network, calculate the loss, and then backward. And here they don't use the scheduler as we see above. And that's it. And now I'm training the network, and the loss seems to decrease, but not quite fast. And that's it, I think. And here they test the model with the evaluation set.
Okay.
Okay, so shall we look at the model? Maybe we look at the model that is declared in here to see here. So they use this function to declare two convolution layer with the value activation function, max pooling, and they use upsample with the scale factor of 2, which means we double the size of the images. Okay, so, and they declare the shortcut connection in the forward function. Here you can see they concatenate the output of upsample and the output of convolution layer number 3. So that is our shortcut right here, and we have another shortcut and another shortcut. So I think that's it for my side. Okay, so I think that's it.
Okay, so thank you. I think that this is not really difficult to understand the notebook, so I hope that you practice more if needed to understand the UNet and all the thing inside that notebook. Okay, so I think that we can stop here, and we will meet together in the next week. Okay, bye bye. Thank you.